Renewable and non-renewable resources. So, first, a natural resource is basically anything in nature that humans find economically valuable. It could be trees, it could be minerals, diamonds, gold, oil, it could be uh, food sources like fish, mushrooms, absolutely anything that humans find to be of an economic value is called a natural resource. Now, these natural resources come in two varieties. They come as either renewable or non-renewable. Now, a renewable resource is one that you can never run out of, that it's naturally replenished. There's always going to be more of it. So examples of this would be like solar energy. The sun is always going to shine. As long as there's a planet Earth, for another 5 billion years, the sun's going to shine. There'll be solar energy. The wind, as long as the sun is shining, it's going
Attention
to make the
students,
wind
the
blow,
school buses will leave
because of
in 5
convection. So
minutes.
there'll always be wind
Please get
energy.
on the buses
As long
now.
as the sun shines down, is going to make, crops are going to make photosynthesis, so there'll always be food. The sun, notice how there's a theme here. It's all about the sun. The sun's going to lift up water from the oceans, drop it down as rain, as pure drinking water. Wood's going to keep growing. So you notice things that are related to the sun, since the sun doesn't go away, tend to be what we call renewable resources. But you don't run out of them. You always have plenty of them. A non-renewable resource, on the other hand, is something that can't be replaced. You get to use it one time and then it's gone. Now you can recycle some of them, but others it's like a one-time use and it's gone. And at least it can't be replaced any time frame that was of any use to human beings. So examples of this would be like fossil fuels. There's a certain amount of oil in the ground. There's a certain amount of coal. Once we burn through it, it's gone and we cannot get it back. Minerals, so if you use a mineral for something, the world's not making more of those minerals for us. At least not any time frame that we can count on. So things like uranium, which is a very useful mineral in terms of nuclear power, once it's gone, it's gone. Helium, used to be you could get helium for like my career, you put in balloons. Now it's just about gone, and the only thing they can use it for is scientific research. Um, so these are things that once it's gone, it's gone. It's non-renewable. Can't get it back. Now, because a non-renewable resource is not replaced, it just makes sense if you keep using it, you are going to run out of eventually, no matter how much you start with. So imagine yourself sitting on top of like $1 million, and you have no plans on making any more money. You just spend what you've got. Well, at first you might think you could never run out of it, but common sense, basic math tells you if you don't replace it and you keep using it, eventually it goes to zero. So there's an end point, and sometimes it's going to be difficult to figure out when that's going to be. So let's just look through some examples of this and see why there can be some confusion, but there should be no confusion over the fact that you will eventually run out of non-renewable resources. That is a mathematic certainty. So, for example, 41% of the world's electricity comes from burning coal. All right. Coal is non-renewable. It was made 600 million years ago. It's not being made any time frame we can use. So how long is it going to last? We're definitely using it, and we're not getting more of it. It's non-renewable. We'll run out. So here's what you got to do. You got to think in terms of what is the extent of it? How much we call it reserve. So how much coal is there that we can actually access? Okay, that's a fixed amount. And then what is the rate at which we're consuming it? And then it's just simple math. So when you're going to run out of it, well, basically what happens is you simply take the amount of reserves that you have, you divide it by the rate at which you're using them, and what you're left with is the amount of time it's going to take to run out of them. It is simple. Take the amount you have, divide it by the rate at which you're using it up, and that's how long you get until you run out of it. So let's look at an example of it. So it is estimated right now that the world reserves of coal is about a little over 1,000 billion tons of recoverable coal. That means coal we can actually get access to. Right now, the world is burning through it at about 8.5 billion tons per year. So let's just do the math, okay? What is the depletion time? Well, if we have a little bit over 1,000 billion tons of reserves and we're using it up at 8.5 billion tons a year, you get 134 years, which seems to you at your age like a very, very long time. But I'm already 58 years old. That's like halfway through that. Okay, so it's not as long as you think. And by the way, the law of supply and demand, as it becomes more scarce, it's going to cost a lot more money. But wait, it's even worse than that. So we can think of the reserves as a fixed amount. In this case, like as a volume or an area. Okay. So think of it this way. So if I make a graph, if this is the time and this is the rate of consumption, I have a fixed area, like an integral. Okay. So this area here is the total amount that's available. And right now, if you have 1,000 billion tons and you're using it up at 10 billion tons a year, you're going to run out of it in 100 years. Okay. Now watch this. What if we use it up faster? All right. So if instead of just using uh, 10 billion tons a year, we use 20 billion years, well, guess what? You don't have to be a genius to see, well, therefore it's going to last half as long. You have a fixed amount of reserves. You're using up twice as fast. It lasts half as long. All right. Well, here's what often happens that confuses matters for people. We discover new reserves. So we don't really know what's there. Geologists have a pretty good sense, but often, we find out, oh, wait, maybe we can recover this, or, new technology arises so we can get at more of it, or we didn't realize that this was a region of the Earth's surface that had, or Earth's crust that had coal in it. Okay. So sometimes we can extend our reserves a little bit. So go back to our first diagram. We thought we'd run out of 100 years. Well, guess what? We developed this new technique. So we have more coal than we thought because we have ways of getting at reserves we didn't think we could reach. Well, that extends the amount of time. This is the source of confusion for people. So they keep changing their mind because we keep finding either more coal or ways of accessing more of it. Okay. So basically what that does, that just means there's a greater amount that you're accessing. So that extends your time. But what happens is as the world develops, we tend to increase our consumption at an increasing rate. And so it actually should be curved upwards, but I'm just going to make it linear because it's hard to draw otherwise. Okay. So what happens then is you can see since this area is fixed, we can't get more of it. Then if this, instead of being level, if this goes up, this area equals this area. So that means instead of lasting 120 years, maybe it's going to last 80 years. So that's basically what happens with non-renewable resources. You can only have them for a certain amount of time, and you can calculate when they're going to run out. And unfortunately, humans are good at math, but we're bad at acting on it. So we know we're going to run out of this stuff. We just don't act on it. We keep going, well, it's 80 years down the line. That's a lot of time. Well, 80 years is not as much time as you think. And if you wait until here to do something about it, you're going to be in trouble. Now is the time to start acting. Okay. So that's the deal with renewable and non-renewable. So let's look at this. Water, drinking water, should be a renewable resource. The sun shines, it picks up seawater, it drops it, it percolates through the soil, it gets cleaned, and now I have an aquifer that has nice clean water in it. Granted, okay, so under normal circumstances, this aquifer would be what we call a renewable resource. So here's my well, I'm going to pump water out of it. So look at this. Let's just say that this aquifer I'm talking about contains 100 million liters, just to make my math easy. And every year 10 million liters comes in, and every year 10 million liters flows out of it. Well, you guess what? I'll always have 100 million liters since the rate of inflow and the rate of outflow equals. And now what's going to happen is I'm going to try taking some of the water out. So what if I took out 4 million liters a year for my community? 10 million comes in, 6 million goes out, but you know what? I still have I still have 100 million liters here. This is a renewable resource because I'm not using it up faster than I get it. But what happens if I pump faster than that? My community grows. Now I'm pumping out 15 million. What happens now is 10 million comes in. I pump out 15 million. Well, guess what? I don't have 100 million liters worth of water in my reservoir. Now I have 95. And then if things keep going this way, I'm going to have 90, 85, 80, and eventually I'm going to run out. And we see this happening. So even though groundwater is normally considered to be a renewable resource, if the rate at which you use it is faster than the rate at which it replenishes, it stops being a non-renewable. It starts becoming a non-renewable resource. Okay. Well, I guess that's just what I just went through, so I don't need to do that. So that's renewable, non-renewable resources. It's a term we're going to be using quite a bit this semester.